We're going to jump straight back into the top traits. If you didn't catch the last video, linky in the corner. My name is Daniel, welcome to Iris. By now, you're probably beginning to understand how important types are to Rust, but sometimes you need to take the data from one type and move it into another type. There's two pairs of traits that do this for you really well, depending on whether you can guarantee the conversion will work or not. From and into are the easiest ways to convert between types, so long as the conversion is guaranteed to work. They require you implement the from and into methods respectively. For an example of how they work, you'll regularly see people turning a string slice into a string in one of these two ways. We can create a string from a string slice, or we can turn a string slice into a string. Though in this case, we need to be specific about what we're converting the string slice into. What's really cool though is you rarely, if ever, have to implement into yourself. You might have realized that the functionality of impl into string for string slice reference is probably identical to impl from string slice reference for string, and the good folks behind Rust realized that too. There's a generic implementation of into that looks like this. Now we haven't talked about where yet, but it's a way of providing type bounds like when we've used colons in previous examples, but where is easier to read when the type bound is a little more complex. This generic implementation simply applies into u for any type where u can already be gotten from t. Simple, but powerful. Because of this, however, you should only ever implement into if and only if you can't implement from. To show you how to implement from, I'm going to teach you one of the best and most common uses for it. At the end of the last video, I mentioned you should keep the error trait in mind. Hopefully you did. If you didn't, here's a link to that video. Now, once you understand from and error, you have access to another incredibly powerful tool in Rust's arsenal, the question mark operator. We've discussed previously that in Rust, we don't use exceptions. When a function can fail, it should return a result type. As you can imagine, when we have deeply nested function calls, all of which can fail, it would get a bit annoying to have to constantly handle each result, extract the data if it's okay, or handle the error if it's not. That's where we use the question mark operator. When used on a result, it will immediately extract the OK variant if the result is OK, otherwise it will return the error variant as a result error from the current function. Of course, it's unlikely that the calling function returns the exact same error type in its result as an erroring function is called. However, if there is a from implementation that can convert them, then the question mark operator will use that to propagate the error. So this is equivalent to this. Sometimes it's just not possible to guarantee that a conversion from one type into another type will definitely actually work. TryFrom and TryInto can help you with possible errors using another feature of traits we haven't yet discussed, associated types. To oversimplify things a little, let's say you're talking to an external system that thinks about pets like this, but your system only cares about cats. We can't implement from pet for cat because not all pets are cats. What happens if it sees a dog? Instead, we implement TryFrom pet for cat. TryFrom is similar to from, except that it can fail, therefore returns a result type where the OK variant is the type we're converting to, which is the type we're implementing it for, and the error type is, there's no error type in the generic or what we're implementing for. It's time to introduce associated types. The official Rust book has a detailed explanation of associated types, but I think the best way to think about them is they're a bit like private static placeholder types. They're similar to generics in that they are defined once and reused throughout a trait implementation. However, you're not leaving the type up to the person calling the generic code. This loss of flexibility comes with two significant upsides, however. First, the trait is easier to use for the caller because it has less or maybe even no generics. Secondly, and relatedly, you are reducing the risk area of making mistakes. So here's how we would implement TryFrom for our cat. And yes, TryInto is automatically provided by Rust for any types that already provide the reverse TryFrom implementation. One thing to note though is, like into, you still need to type hints to Rust what the generic parts are, but because they're now inside a result, it's a little more verbose. However, we only need to specify the OK variant of the result. The error type can be inferred from the TryFrom associated type. How clever is that? To ask Rust to infer a type, we use an underscore. We have talked a little bit about referencing already. In Rust, we have this concept of ownership. A variable owns the data stored in it, and when the variable goes out of scope, its owned data is cleaned up. To save having to pass ownership around or creating lots of clones of data, you can borrow the data owned by another variable. When you do this, you're given a reference to that data. In many ways, references are like pointers in other languages, except that the compiler will check to make sure a reference never outlives the owner of the data it's borrowing. That is the borrow checker thing that you've probably heard about. When a reference goes out of scope, only the reference is cleaned up, the data it was borrowing isn't. You can have any number of immutable borrows, or a single mutable borrow. Rust has other kinds of pointers too though, including smart pointers. These point at some location in memory too, however, they also provide additional functionality to the data. The example I keep coming back to is the string type, which is a smart pointer to a string slice that exists on the heap. Not only is it the only way to manipulate string slices, but it also handles things like how memory is freed when the string is dropped. A simpler smart pointer we haven't covered yet is boxt, which allows you to store any arbitrary data on the heap and deals with allocating and deallocating that memory for you. In Rust, it's even possible to write code that manipulates memory directly and even handle raw pointers, but it's actually very rare to need to do this. We will cover this later when we talk about unsafe Rust, which I promise is less scary than it sounds. But I digress. These next few sections deal specifically with traits that make references and smart pointers more malleable. Borrow can allow you to borrow the data of one type as if it's another type, and BorrowMut allows you to borrow that data mutably. All types implement borrow and BorrowMut for themselves, allowing you to borrow T and get a reference to T, and mutably borrow T and get a mutable reference to T. However, you can also borrow a type as a different type. For example, you can borrow string as if it were a string slice. As I mentioned, string is a smart pointer to a string slice stored on the heap, and it implements borrowStringSlice to allow us to borrow the data as if it were a string slice type. You can also provide further implementations of borrow yourself, allowing you to borrow the same data as if it were a variety of types. However, there are some important restrictions that effectively mean you should only implement borrow for types where the internal representation remains the same. This means you should never implement borrow when you only want to return a part of the underlying data. A common pattern in Rust is to use wrappers around other types. This is the new type pattern. Imagine you want to store an email address. Obviously, a sensible type to store that data in might be a string. However, there's no validation on creating strings, so how do we know if any given string contains a valid email? For that, we can wrap the string in a new type. Here we'll create the email type as a tuple struct with a string. And we'll add a method for validating if a string is a valid email. A quick note here, email validation is very complex. If you're coming from another language where you use some crazy regex, you're probably doing it wrong, I'm really sorry. For basic validation, I recommend making sure that there's an @ symbol and it's not the first or last character. Or you could write your own parser, or you could use someone else's validation library. And yes, this is because I use plus in my email address all the time, and it annoys me when I can't do that. Finally, let's add a constructor function that takes an existing string, validates it, and returns a result with either the valid email or an error, which I'm leaving out of the code on screen for brevity, though if you are curious, obviously check the RS book link in the description. Now that we have our email type, what if we want to use it as a string? This is where borrow can come in handy, as we can use it to return an immutable reference to the underlying data. BorrowMut does exactly the same thing, but gives you a mutable reference instead. In our email example, we could implement it to get a mutable reference to the underlying string, but in this case, should we? Allowing mutation of the data inside of the email would bypass the logic of our email type that guarantees the email address is valid. Now, there's some important caveats to borrow and BorrowMut. if a type implements borrow where it's true that x is equivalent to y, then it must also be true that a borrow of x is equivalent to a borrow of y. If your type implements EQ, then your borrow type must also implement EQ. Furthermore, if x is greater than y, then a borrow of x is greater than a borrow of y, etc. Finally, if our type implements hash, then if the hash of x is equivalent to the hash of y, then the hash of a borrow of x must be equivalent to the hash of a borrow of y. There are no compiler checks for these caveats. You need to be sure that it's true when you implement borrow, and as you can probably guess, borrow really only works when the exact binary representation of a value is the same between the types, making it less useful for compound types. Knowing about this behavior is important, but I actually don't think I've ever implemented borrow outside of working on Iris. I prefer to rely on traits in the next two sections, depending on the circumstances. So now we have a way to borrow an entire type as a different type, but we won't be able to do that with more complex compound types. If we have a complex compound type and want to internally reference a part of it, we can use one of these traits instead. Remember earlier we had our cat type, which only had a name. We could, if we wanted, implement AsRef string slice for cat so that it can be used in place of a reference to a string slice. Arguably, we could make this code even more friendly by changing the cuddle functions to take a generic and then calling AsRef in the function itself. This code looks a little scarier, but once you get used to seeing code like this, you can write far more flexible and easy to use code. AsMut is essentially the same as AsRef, but for mutable references instead. We mentioned earlier that when referencing, you're creating a pointer to another piece of data, but when dereferencing, you're moving back from the reference to whatever was underneath. This can be especially useful when working with references to references or references to values that are copy. See the previous video. We've also talked a bit about smart pointers, which are not references, but a way to wrap data with additional functionality. To get inside a smart pointer, we can use the deref trait, and ergonomically, dereferencing can happen automatically. This is why a reference to a string can be used as if it were a reference to a string slice with no extra work. When a smart pointer wraps a mutable type, although remember string slices are not themselves mutable, you can also implement the DerefMut trait, but you need to think carefully about when it's appropriate to do this. Let's return to our email type. It makes sense to allow our email to be used as an immutable string, so let's implement deref for it. Let's think about this differently though. What if instead we dereferenced to a mutable string? Our email type here does some rudimentary validation. If we allowed mutability of the inner string, we allow people to change the email to be invalid and lose the benefit of the email type. Let's not do that. I personally prefer deref to borrow because it can be triggered automatically. We don't need to call extra methods, just pass a reference. I just have one more trait to show you. This one didn't really fit in anywhere else, but I kind of love it. Particularly one of the functions that gets used fairly heavily with it. I hope you'll see why in a moment, but here we go. Rust is very good at cleaning up after itself, especially when you use the standard library. If your variable allocates heap memory, that memory is released when the variable goes out of scope. If you open a file to read or write, it's closed when the file handler goes out of scope. If you start a TCP connection, it's ended when the handler goes out of scope. The Rust standard library is achieving all of this with the drop trait, and you can implement the drop trait yourself. When a variable goes out of scope, if it implements the drop trait, then the functionality on that trait is called. This allows you to write cleanup code for the type implementing the trait. Depending on the type of programming you do, you may not need to think very much about this trait, except there is one thing worth considering. Each of those examples I just gave is blocking. That means that the program will have to wait until whatever the drop method of the drop trait needs to do is complete before continuing. You may want to be mindful of this when you allow things to go out of scope and be aware of what any library code you're consuming might be doing. Most of the time it isn't worth worrying about, but if you do find yourself wanting to be precise about when things get dropped, then let me introduce you to my all-time favorite function in any language, standard mem drop. Here it is in full. Yeah, that's not a mistake. It has one generic variable and no function body. Remember that variables in Rust are owned by the function that they exist in, and when they leave that function, they're dropped. The intention of this function is that at the exact moment you want to cause a variable to be cleaned up, you pass ownership of that variable into this function, and the function ends immediately, and if the variable has a drop implementation, then that code is run then and there. There's still, I think, two big traits to talk about, iterator and inter-iterator, but before we get to them, we're going to need some things to iterate through. So next time we'll look at collections. Let me know if I haven't covered one of your favorite traits in the comments. If you're enjoying this, don't forget to impl drop for like. Drop me a like. And if you want to see more, hit the subscribe button. And I'll see you next time.